Welcome back to another video. In this video, we're going to talk about rational functions. Can y'all see it? My light is kind of reflecting up here. Sorry, I'm making the best of what I got. All right, so rational functions. What exactly is a rational function? A rational function is a function f of x of the form p of x over q of x, where p of x and q of x are polynomials and q of x is not equal to 0. So what does that mean? Basically, a rational functions are fractions where you have a polynomial in the numerator and a polynomial in the denominator. Alrighty. And so what we're going to look at in this video is we're going to look at a couple of parent functions of rational functions and how to graph them. Alrighty. So the first parent function of rational functions is called the reciprocal function, and that is the function that takes the reciprocal of whatever you plug into it. So f of x equal 1 over x, that's your reciprocal function. So whatever you plug in, so if I was to make a t-chart, if I was to plug in my favorite 5 numbers, these are my favorite 5. If I was to plug in -2, I would get 1 over -2, which is -1/2. If I was to plug in -1, I would get 1 over -1, which is -1. If I was to plug in 0, 0 in the denominator is undefined, so that would be undefined. If I was to plug in 1, I would get 1 over 1, which is 1. And if I was to plug in 2, I would get 1 over 2. So whatever you plug in, you're taking the reciprocal of it. Now, if I was to graph this, my graph will look like, so -2, 1/2. So let me put my little marks on here. So -2, -1/2 would be about right here. -1, -1 would be here. 1, 1 would be here, and 2, 1/2 would be here. Now I know these 4 points don't tell the full story, but if we were to continue, the graph will look something like this, and something like this going through those points. So basically, it breaks up into 2 separate parts. So this is what's called a discontinuous graph. That means it's not continuous because I'm not able to draw the whole graph without picking up my pencil or my marker in this case. Since it was undefined at 0, we end up with a break in the graph at x equals 0. So I'm making a dashed line here, and that's called an asymptote. So rational functions have asymptotes, and it's just basically a break in the graph. Alrighty, so some of the things I need to be able to determine about this graph is like, what is the domain of this graph? So D for domain, that means what are all the x values? Remember, domain stands for x values. What x values are on this graph? So if I look for my smallest x value, because the arrow goes this way, that means it continues to go and go and go like the Energizer Bunny. So that would be -infinity. So because it's going in a negative direction. And then it gets here to close to this asymptote and it goes down. So what this asymptote means is that this graph is getting really close to this line, but it's not touching it. So it's almost like a magnet. It's attracting it to the graph, but it's not attaching. So a magnet attracts something and then it attaches or connects. In this case, it's not going to connect. It's going to draw it really close but not connect. So it stops at 0. And 0 is not included because it doesn't connect. And then it picks back up at 0. So I'll have a U and a 0, and then this arrow continues in that direction, so that means it goes to infinity. So this is how you will write your domain: -infinity to 0, union 0 to infinity. And you will need to be able to find the range as well, the range of the y value. So what is your smallest y value on this graph? Well, because it's going down with the arrow, that means the smallest y value is -infinity, which isn't a value, it just means it keeps going in the negative direction. And then it comes here and it stops here. You notice that there's another asymptote here. We didn't talk about it at first, but I'm making a dashed line here. There's another asymptote here because the graph gets really close to that line, but it doesn't touch it. So it goes to 0. Since it doesn't touch 0, you'll put a you'll put a parentheses. Then it picks back up at 0. right above 0 and it goes up to infinity. So that would be your range. The other thing you would need to be able to identify is where is your horizontal asymptote and where is your vertical asymptote. So here's your vertical asymptote. That's your vertical break in the graph. So where does the graph break up vertically? So there's a vertical asymptote at this line right here, which is the line x equal to 0. And then there's a horizontal asymptote at this line, which is the line y equal to 0. Alrighty, so those are your two asymptotes. When you talk about discontinuities or where the graph is discontinuous, you talk about where it's discontinuous in terms of the x values. So you would say this graph is discontinuous at x equal to 0. And that's this line right here. And basically it's the same as the vertical asymptote. Now this graph is considered to be, or this function is considered to be an odd function. And it's an odd function because it's symmetric with respect to the origin. So now what does it mean to be symmetric with respect to the origin? That means if I was to take this graph in one quadrant and rotate it 2 times clockwise or counterclockwise, it doesn't matter. If I get that same graph, then it is symmetric with respect to the origin. So I got a sheet of paper here and I'm gonna show you what I'm talking about. So if I was to take this graph here, that's in the first quadrant, I'm just sketching that part of the graph on there. It's kind of hard to see because it's close, but there's a curve going in there. If I take it and I rotate it 2 times, that's 1 time. I rotate it 2 times. You see I get the same graph, that curve going off in there. If that's the case, that means it's symmetric with respect to the origin. If it's symmetric with respect to the origin, it's an odd function though. So this reciprocal function is an odd function. All right. So this is your reciprocal function. This is how you get the points. You just plug in numbers, take the reciprocal of it. We graphed it. So this is what the graph look like. There is a break in the graph, both vertically and horizontally. Those are called asymptotes. So you need to know how to identify those. And we looked at this to figure out what is the domain and what is the range of it. So those are just basic characteristics of the reciprocal function that you need to be able to look at and determine. We want to take a look at some examples, and in this particular example we want to graph y equal 1 over x plus 10. Now this almost looks exactly like the reciprocal function, which we just talked about, f of x equal 1 over x, except there's one little difference, and that one little difference is that we're adding a number with that x. And so what's happening is we're transforming the graph. We're applying a transformation to it. So the same transformations we've been talking about in the previous chapters, those same transformations still apply to this function. So whenever you add a number with the x, you're going to move the graph horizontally. So you're going to move it either left or right. Okay. So whenever you add it with the x, since it's a horizontal move, you do the opposite of what you think you would do. So because it says plus 10, that means you're going to move this graph left 10 units. Alrighty, so you take the graph of 1 over x and you shift it to the left 10 units, okay? So I'm just going to sketch it. I'm not going to go through and find the points because I just want you to be able to look at this and to be able to tell me what is the transformation that's being applied to that parent function, the reciprocal function. So our original graph was here, right? It was in these windows. And I'm not putting exact points, but I'm going to get another color here. And I'm going to show you how the graph will be changed. So I need to make this a little longer because I got to go 10 units. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means my new vertical asymptote will be here at x equal to negative 10. And so now these will be my new windows. So my graph would now look like this. And I'm just sketching it. I have in no way found points and made it as accurate as it could be. But if I wanted to find points and get exact points, then I would just plug in numbers for x, such as negative 10. When I plug in negative 10, I get 1 over 0, which is undefined, and that lets me know that I have a vertical asymptote there. I could plug in negative 9. If I plug in 1, negative 9 plus 10 is 1, I get out 1. So if I wanted to find exact points, I could do it that way. Alrighty. So all I want you to be able to do is look at this and say, okay, this is the reciprocal function, but we added 10 to it with the x, so that means it's going to shift that reciprocal function to the left 10 units. So let's look at another one. For this one, we want to grab y equal 1 over x plus 3. So now we do have the reciprocal function, but we're adding 3 to it this time. And we're not adding the 3 with the x. We're adding it outside of the x, outside of that function. So what this does is this takes the reciprocal function and shifts it up 3 units, because anytime you're adding outside of the function, that's a vertical transformation. So again, I'm not finding exact points. I'm just going to sketch it because I want you to be able to just look at this and say, okay, I know what the reciprocal function look like, and I know that this plus 3 means to shift it up 3 units. So this will be my new horizontal asymptote, and this is still my vertical asymptote. So now these are my windows. So it'll be this window and this window. So my graph would look like that, just sketching it, right? Again, if I wanted to find more accurate points, I could plug in values for x and y, such as 1. 1 over 1 is 1 plus 3, which is 4. So I have a point at 1, 4. So if I wanted to know the exact points, I could find them by plugging in values for x and y. Now we're going to take a look at another parent function, which is 1 over x squared. This one doesn't have a name like the reciprocal function does, but it looks really similar to the reciprocal function, except you're squaring the x that's in that denominator. Alrighty, so I want to look at this and I want to graph it by using a t-chart, picking my favorite 5 numbers and plugging them in and see what I get. So if I plug in -2, I get 1 over -2 squared, which is 1/4. If I plug in -1, I get 1 over -1 squared, which is 1 over 1, which is 1. If I plug in 0, I get 1 over 0 squared. Again, that's undefined. If I plug in 1, that's 1 over 1 squared, which is 1. If I plug in 2, that's 1 over 2 squared, which is 1/4. So now if I were to plot those points at -2, I'll be at 1/4, which is about right there. At -1, I will be at 1, which is here. That's -1, 1. At 0, I have another asymptote because it's undefined. So there's a vertical asymptote there at 0, and that's a dashed line. I don't know if y'all can really see it, but I'm making a dashed line wherever there's an asymptote. At 1, we'll be at the point 1. And then at 2, we're at 1/4, which is down here somewhere. So now my curves are in different quadrants. So now my curve is up here in the second quadrant and over here in the first quadrant. So I had one in the first quadrant before, but basically I had a curve in the third quadrant with the reciprocal function, but it's now up here in the second function. So we end up with 2 curves, both above the x-axis, and that's because when you square, you get positive numbers out. So this is what the graph of 1 over x squared would look like. If we were to find the domain would be the same as the reciprocal function, because this arrow means it goes to -infinity. It stops here at the y-axis, which is 0, picks back up at 0, and goes to infinity. So your domain would be the same. Now, your range would actually be different, because with the reciprocal function, it continued down in a negative direction. But with this function, there's nothing underneath the x-axis, so everything is positive. So where does it start? It starts here. So again, this is a horizontal asymptote, meaning the graph gets really close to this x-axis, but it doesn't touch the x-axis. Alrighty, so it will start at 0, and because it doesn't touch the x-axis, you will put a parentheses around 0, and then it continues on to infinity. So that would be your range. This graph is also discontinuous at x equals 0. And this graph is a reflection about the y-axis. So this graph is reflected. If I was to take the y-axis and fold it up, those quadrants, what's in those quadrants, will lay directly on top of each other. And so because of that, this graph is an even function, or this function is an even function, because it's symmetric about the y-axis. And one last example we're going to look at, and that's going to be, we're going to graph f of x equal 1 over x plus 2 squared minus 1. So now this one is similar to the second parent function we looked at, 1 over x squared, because it has the x in the denominator and the square. So there are also transformations applied to this graph, and I just want you to be able to look at it and tell me, how do these transformations affect the graph, and then just give a sketch of it, right? So when we add 2 inside the parentheses, remember that's a horizontal shift. It's going to go either left or right, whichever way. I don't know which way, y'all. So when you add 2 inside the parentheses, that's going to be a horizontal transformation. It's going to go either left or right. I think I'll get those right, left or right, one way. Anyway, but because it's plus and because it's horizontal, it does the opposite of what you think it's going to do. Plus 2, you would think it go to the right, but since it's inside those parentheses, it actually goes to the left 2 units. And then anytime you add or subtract outside of the parentheses, it's going to shift it up or down. And since this is a minus 1, it's actually going to shift the graph down 1. So remember, with that function, we had a vertical asymptote here and a horizontal asymptote here, and the intersection of those asymptotes was the origin, the point 0, 0. But now since we're going to shift the graph left 2, so if I go left 2 here and negative 2, now my vertical asymptote is here. And if I shift it down 1 here to negative 1, then my horizontal asymptote is here. So now my graph, I'm going to use a different color, is in this window. In this window. And again, I'm just sketching it, right? If I wanted to get more accurate points, I could get those by plugging in numbers here. I could plug in negative 2. If I plug in negative 2 plus 2 is 0. 1 over 0 is undefined. So that's why my vertical asymptote is at negative 2. I could plug in, let's say I could plug in negative 1. Negative 1 plus 2 is 1. 1 squared is 1. So 1 over 1 is 1. So 1 minus 0 is 0. So at the point 1, it crosses, or negative 1, it crosses at 0, which you can see on my graph, even though I was just sketching it. And so because it's a reflection across the y-axis or across your vertical asymptote, we're going to have that same point over 1 unit in the other direction from that vertical asymptote. So again, I just want you to be able to look at it and determine how the graph is transformed by these different operations, how they affect the graph. If you have any questions whatsoever, be sure to include them in the comments below. I hope this video helped you. If it did, hit the like button. And thank you for watching and tuning in. And be sure to check out the next video, which is how to find the vertical and horizontal and oblique asymptotes by just looking at the equation or the function in symbolic form. Thanks for tuning in.